Welcome back. Our next video lecture is going to be about, we're going to cover Chapter 2, Section 7, which is entitled Graphical Integration in Motion Analysis. This is a little more calculus, added on to what we've already introduced in Chapter 2, and I know that some of you are still new to calculus, so I'm going to try to be very clear in this section on what exactly you need to know in order to solve physics problems for this chapter. Okay, so here is the first key idea. Integrating acceleration gives change in velocity. Let me explain that. Integrating is a new calculus term we're going to be using here. Let me start by reminding you of something, namely the definition of acceleration from Chapter 2. Acceleration is defined to be the derivative of the velocity with respect to time. That's what this equation A equals, or defined to be, dv over dt, which we often just say dv dt. Okay? The derivative of the velocity with respect to time. Also called rate of change of velocity. Remember those words too. That's the definition of acceleration. By definition, acceleration is derivative of velocity with respect to time. Now, one of the things you'll learn in your calculus classes, it might be late in Math 110 or sometime in Math 111, is a very important theorem in calculus, so important it's called the fundamental theorem of calculus, which tells us that there is a mathematical inverse operation to differentiation. And it's called finding the antiderivative, or it's also called integration. And so the idea is that if acceleration is derivative of velocity with respect to time, then velocity is the integration of acceleration with respect to time. Or to be more specific, change in velocity, that's what the quantity here on the left is. V1 minus V0 means a difference in two velocities, or a change in velocity. Namely, V0 represents the value that the velocity of your particle had at some initial time t0, and V1 represents the value of the velocity your particle had at some later time t1. And so V1 minus V0 is a change in velocity. And that's given by this weird-looking expression right here. And this long, drawn-out symbol out front looks kind of like a stretched S, because an integral, and that's the symbol for integration, is a kind of, very fancy kind of sum, S-U-M, or addition. Okay? The end of the day, integration boils down to a kind of addition. And so the symbol for doing an integral is a stretched out S for a sum. And then you put at the lower end what's called the lower limit of the integral. And we're going to integrate with respect to the time variable. So it's going to be a time value, and it's time t0. And then the upper symbol on the integral symbol is the upper limit of the integral, in this case, the ending time t1. So what we have on the right is the integral from time t0 to time t1 of the acceleration, a of t, and dt means with respect to time. So, in words, velocity change equals integral of acceleration. So, if we can perform this process called an integral, specifically the integral of the derivative with respect to time, we can find out how much a particle's velocity has changed over that time interval. Now, you may be thinking, okay, but I don't know how to do this process called integration, right? How do you do it? Well, here's the main thing you have to know for this chapter. The integral of a function equals the area underneath it when it's plotted. Okay? So we're integrating acceleration with respect to time. So we need to be given a graph of acceleration on the vertical axis and time on the horizontal axis. And then we got to mark out the starting time, wherever that is based on the problem, t0, and the ending time, t1. Again, we have to be given those on the problem. Then the area between the plot of the acceleration and the time axis, starting at t0 and ending at t1, and that's the area that you see shaded in light blue in the picture here, that area is the integral of the acceleration. Okay, so here we have it. This is the main thing you need to know. If you need to integrate acceleration from time t0 to time t1, you merely have to find the area between the acceleration graph and the time axis from t0 to t1. Now, this way of doing an integral is fine if the graph of acceleration versus time has simple area shapes underneath it, like you see here, right? These straight line segments for the area graph. Then this area that's shaded in right here is just a combination of rectangles and triangles. We'll do an example problem in a minute, so you'll see more about that. But as long as that area under the curve is a simple shape like a rectangle or a triangle, we can use this procedure for finding an integral. All right, now if this kind of reversing the definition of acceleration can be used to find a velocity change, let's take it another step further. Okay? Here comes the next key idea. We can integrate velocity to get change in position. Why? Because let's remember the definition of velocity. Velocity, by definition, is the derivative of position with respect to time. Velocity is derivative of position. So using the fundamental theorem of calculus, we can invert it. And position change, x final minus x initial, x1 minus x0, is given by the integral from the starting time t0 to the ending time t1 of the velocity with respect to time. So position change equals the integral of velocity. But then the integral of the velocity is just the area between the velocity plot and the time axis. So now you need a graph of velocity versus time. And you have to be told the starting time t0 and the ending time t1. And you have to have a graph so that the area underneath it is simple shapes like rectangles and triangles. And you can find that area, and then you can find the integral of velocity, which will give you the change in position. So these are the key ideas. Let me show you how that's going to work by doing a Wiley plus type problem as an example. Okay? This is our fifth example in chapter 2, so it's example 2.5. And it involves integrating velocity to find change in position, what I was just talking about in the previous slide. And I am doing now for you a particular problem taken out of your textbook, Fundamentals of Physics. HRW is Halliday, Resnick, and Walker, the author's initials. And it's the problem number 66 in chapter 2. And it's an application of physics to a real-world scenario. And it goes like this. In karate, if you do what's called a forward punch, the fist begins at rest at the waist and is brought rapidly forward until the arm is fully extended. This is one of the karate moves. We are going to be given, in this problem, the speed v as a function of time of the fist of a person doing this karate move. Okay? And so here we have a graph. Velocity in meter per second. Good old SI units for velocity, no problem there. Time in milliseconds. Watch out for that. That's not an SI unit of time, although apparently for this kind of problem, the millisecond is a convenient unit, presumably because the karate move happens very rapidly. So the time interval is very short. And we have a graph that we are given. So somebody has already done measurements of the speed as a function of time of the fist in this forward punch karate move. Right? They've already done some analysis, and so they're giving us this plot. with graph and a grid and numbers on the axes so that we can find area underneath this graph. All right, now here comes the first question. How far has the fist moved at time t equals 50 milliseconds? So what that really means is if the move starts, if the fist starts moving at time 0, which seems pretty clear, there's 0 on the time axis, then go up to 50 milliseconds and tell me how far the fist has moved in that time interval. So now what we're saying is that t0 is 0 and t1 is 50 milliseconds. And so what we want to find is, the interpretation is delta x. All right, so doing this example, let me do blue here. Okay, we have a sketch. The sketch that's important in this problem is the plot of v versus t. Now let's tabulate what we're given. And the main important thing we're given is the plot. That's what we're going to use to answer this problem. Okay? So again, the plot is the key thing. But we'd better observe something about the plot since we're going to have to get right into the details of it. Let's look at it again. Bring it back. And you would find this problem on Wiley Plus, and you should be able to zoom in so that you can see the grid lines and so forth carefully. Okay? But what we have to figure out are what the scale is. What is the grid spacing, both on the y-axis and the x-axis? Okay? All right, now, here's an important statement. The vertical scaling is set by this number, v sub s equals 8 meters per second, right? That's what it says. So we have to figure out how to interpret that because we're going to have a lot of graph problems to do as homework, and this is going to be a typical approach. They're telling us the scale on the vertical axis, and we have to figure out how to interpret this. So what they're telling me is that this number right up here, which is clearly at the top tick mark on the vertical axis, is 8 meters per second. So we have to look very carefully at the grid spacing on the vertical axis, and we see we've got the major grid tick marks there, and there, and there, and at the bottom and at the top. And if the top amounts to 8 meters per second, then each of those major tick marks, since the bottom is 0 meters per second, each of those major tick marks must be 2 meters per second. So that I start at the bottom with 0, and then the first major tick mark is 2 meters per second, then the next major is 4, then the next major is 6, and the last major tick mark at the top is 8 meters per second. But then there are 1, 2, 3, 4 minor tick marks between 2 major tick marks. And if the distance between 2 major tick marks is 2 meters per second, then the distance between each minor tick mark, which is the grid spacing on the vertical axis, must be 0.5 meters per second. So let's put that observation here on our work. Okay? Each space on the vertical axis equals 0.5 meters per second. Now we got to do the same thing on the horizontal axis, which is time. So let's look at that. Now note the time is given to us in milliseconds, so we're going to have to convert that to the SI unit of time, or seconds. But you can see some tick marks or grid lines are labeled on the time axis. There's 0, then 50 milliseconds, 100 milliseconds, 140 milliseconds. So let's look between the 0 and the 50. 50 is the 5th horizontal grid line. So each of the grid spacings along the horizontal axis must be 10 milliseconds, right? 10, 20, 30, 40, 50. Okay, so each space on the horizontal axis is 10, now watch the units carefully, millisecond. You would need to convert that to seconds. It's 0.010 seconds. Okay? That's very important to using this graph in this problem. All right. Now let's explain the physics that we're going to use to do part A. It asks us how far the fist moves between t equals 0 and t equals 50 milliseconds. So the physics idea is the one on the second slide I showed you. The change in x, we're going to interpret that to mean distance in this problem, is given by the integral of the velocity with respect to time, v of t dt, from the initial time to the final time. And that integral of velocity with respect to time is area under plot of v versus t, velocity versus time. The initial t, 0. The final t, since it asks at 50 milliseconds, is 50 milliseconds, which is, as you can convince yourself, 0.050 seconds. That's the upper limit. So, we have to find the area under that graph that we're given between the velocity axis and the time axis, and between time 0 and 50 milliseconds, or 0.05 seconds. So now we go back to the graph. And what I find convenient to do here is, let me get rid of some of the clutter on my picture, is to simply break up, or to draw onto the picture, break up the area under the graph into simple shapes. For example, there's a simple shape that's a triangle between 0 and 10 milliseconds. And then between 10 and 50 milliseconds, there's another shape that's just a rectangle, and sitting on top of that rectangle is a triangle. Okay? And that's all the area between 0 and 50 milliseconds. So it's those areas I have to find. There are 3 of them, 3 separate shapes, and I have to find their areas and add them all up. I find it convenient to label the areas. Let's label that triangular area 1, and that rectangular area there 2, and then this other triangular area here 3. And you just have to look very carefully at those shapes, and you have to remember a little bit about geometry, like what's the area of a rectangle, what's the area of a triangle. Okay, so let's find the area for shape 1. It's a triangle, so that's 1/2 base times height. Remember that little formula for the area of a triangle? 1/2 base times height. 1/2, okay, back to the graph. Base means right here, the bottom part, doesn't it? Right? For that little, I'm looking at that little triangle down there, triangle number 1. And you have to just see, oh, well, that is 1 grid mark along the time axis, which is 10 milliseconds, which is 0.01 seconds. So for the base, 0.01 second. Notice the unit, it's seconds. The height is right there. Back to the little triangle number 1. The height is vertical, straight up that one side. Now I have to use the velocity grid to get that height. It's 1, 2, 3, 4 little tick marks. Each little tick mark is 0.5 meters per second. 0.5 times 4 is 2. So the height is 2 meters per second. Notice the units. I strongly, strongly urge you to put those in. Because when I simplify the units, I see a second and a per second cancel, and I'm going to get a number with units of meters, which is what I should get for a delta x. And you just multiply that out. You get 0.01 meters. And that's the area of triangle number 1. All right, the next shape, let's go back to the graph, is rectangle labeled 2. And the area of a rectangle is just base times height. So let's just go straight to those numbers. So you got to get the base now for this rectangle right here. Look carefully, it goes from 10 milliseconds to 50 milliseconds, so that's actual width is 40 milliseconds. Put that in SI, 0.04 seconds. And then the height right here. Oh, it's the same as that triangle number 1, isn't it? And that height is 2 meters per second. Again, the second and the per second cancel. And you multiply that out, and you get 0.08 meters. And then the only thing you have left is the area for shape number 3, which, back to the graph, was that triangle sitting on top of rectangle 2. So now we're back to a triangle. Area, again, is 1/2 base times height. The base is right here. The height is right here. So that's 1/2. Looks like the base is 40 milliseconds. So 1/2, 40 milliseconds. Convert that to seconds, 0.04 seconds. Now, what's the height? Got to look carefully. Looks like it's 1, 2, 3, 4 tick marks along the v-axis, which is another, remember, 2 meters per second overall. So again, second per second cancel, so I have something with units of meters. And you multiply that out, you get 0.04 meters. Now I've got those 3 areas. I need to find the total distance traveled by the fist between t equals 0 and t equals 50 milliseconds. Add the 3 areas we just calculated. 0.01 meter plus 0.08 meter plus 0.04 meter. Right? That came from area 1. That came from area 2. And that came from area 3. And of course, they're all in units of meters, and you can add them then, and you get 0.13 meters. And you have found how far the fist has moved in a karate punch in the first 50 milliseconds. Okay? So it's really just geometry once you understand the idea that you can find delta x by doing this thing called an integral of the velocity with respect to time. And that integral is just an area under a curve. Now let me talk you through part B, but I'm going to let you think about the details yourself. Because it's the same idea. How far has the fist moved when the speed of the fist is a maximum, right? Maximum, of course, means biggest. So we got to be able to look at the graph and see when the maximum occurs. First of all, the maximum clearly is right up here. When time is that? I think it's right there on the time axis. That turns out to be, if you read your time axis carefully, 120 milliseconds. Okay? So I need to find delta x between t equals 0 and t equals 120 milliseconds. So it's, again, just area under the curve, but now I've got more area. Okay? Just got more area. I've got all those areas 1, 2, and 3 that I had already. But now I've got to break up the rest. And you got to be careful here. And note that you go straight up there along at t equals 120. And then just start dividing up the area into simple shapes. In this case, triangles and rectangles, as I just did. And then I'll label them. Let's label that area for that rectangle 4. And the area for that triangle right there, 5. And the area for this rectangle down here, 6. And the area for this triangle up here, 7. Okay? And then you have to find areas 4, 5, 6, and 7. And then you got to add all the areas between t equals 0 and t equals 120 milliseconds. So you got to add area 1, 2, 3, 4, 5, 6, and 7. Okay? But it's really the same idea. Whoops. Get that up there. so that you can check yourself. I'm going to tell you what answer you get when you do part B. Okay. We're finding delta x between 0 and 120 milliseconds. That's 0.12 seconds. And we're integrating v of t dt. And we're just going to find area under curve. All right, you ought to try it for yourself. I will give you some guideposts along the way. Area 4, I get to be 0.16 meter. Area 5, 0.02 meters. Area 6, 0.15 meters. And area 7, 0.0375 meters. I'm keeping extra digits because it's an intermediate step. I'll round my final answer to 2 significant figures. So delta x then is at all 7 areas. When you do that, I get 0.4975 meters, which I will round to 2 sig figs, 0.50 meters. So your fist has moved a half of 1 meter in going from 0 to when it's going fastest. And of course, half a meter is about like this, which seems reasonable for the motion of a human being's arm in a karate move. So we can do a little what I call a summarize at the end, which is also kind of like just a check that the answer makes sense. And if I'd gotten something like some really, really tiny number, like 0.02 meters, well, that'd be 2 centimeters. That'd be like this far. Doesn't seem reasonable for a karate move. Or if I'd gotten 2 meters, which I can't even spread my arms that far apart. That doesn't seem possible for a human arm, right? But a half a meter seems reasonable. So that's how you do a problem in chapter 2 when you are given a graph of velocity versus time. You can find the area underneath it to find delta x. Or if you're given a graph of acceleration versus time, you can find the area under that to find the change in v, velocity. Both those ideas are very helpful. And that's all for today's video.